In previous few lectures, we have seen the discussion of classical theory and quantum theory of diamagnetic material and paramagnetic material. In other words, you can say that we have already discussed in very detail the diamagnetism and paramagnetism by both the classical concept and quantum mechanical concept. Now from today, we will see the discussion of the ferromagnetism. And in this regard, again, first of all, we will learn the classical theory of ferromagnetism, and after that, we will see its quantum theory. Actually, when you say classical theory of ferromagnetism, that means you are talking about the Weiss theory of ferromagnetism. In fact, in 1907, Weiss has proposed a molecular field theory to explain the spontaneous magnetization of ferromagnetic material. Actually, you know, the transition metals like iron, cobalt, nickel, which are actually crystalline solids, actually such type of materials exhibit magnetization even when the magnetizing field is removed. If you place the material inside a magnetic field and you remove the magnetizing field, then it is seen that the material like Fe, Co or Ni, these type of materials exhibit the magnetization even in absence of the magnetic field, or you can say after the removal of the magnetizing field. Actually, the magnetic field which remains in the specimen even when you remove the magnetizing field, that is called a spontaneous magnetization. Okay? So you can define a ferromagnetic substance in this way, that these are the materials which possesses a spontaneous magnetization. So the spontaneous magnetization is the very specific property of ferromagnetic material which differentiates it from the diamagnetic material and the paramagnetic material. In fact, whenever we talk about magnetic material in practice, that means ferromagnetic material. Okay? So I have mentioned here that you can see the materials which exhibit magnetization even when the magnetizing field is removed. That is called are ferromagnetic materials. Okay? For example, as I have told you that these crystalline solids, Fe, Co and Ni are ferromagnetics. And the ferromagnetic substances possesses magnetic moment even in absence of external magnetic field. And that is called actually the spontaneous magnetization. Okay? And it is actually this spontaneous magnetization, you will see this will be stable only below a particular temperature for a given material, which is called Curie temperature. This fact that what I am saying here, that the spontaneous magnetization is stable only below a critical temperature which is called Curie temperature. This we will see actually at the end of our lecture today, when we will explain this Weiss theory in a quantitative manner. Then you will see how we can say that this spontaneous magnetization is stable only below a particular temperature for a given material, which is called Curie temperature. Okay? So now let us see the classical theory, which is actually called the Weiss theory of this ferromagnetism. Actually, Weiss has provided the classical theory of ferromagnetism just on the line of Langevin theory of paramagnetism. Using the expression for paramagnetic material in Langevin theory, Weiss has provided the classical theory of this ferromagnetic material. So what is the basic difference? According to Weiss, in case of ferromagnetic material, an internal magnetic field is also produced when a ferromagnetic material is magnetized. If we'll let us consider that this is a specimen of ferromagnetic material and it is placed in an external magnetic field of intensity, let us say H. Then at a point inside this material, the effective magnetic field intensity is not H, but due to the magnetization of the material, an internal field is produced here. So, the total magnetic field intensity at this internal point, let us say P, is the sum of the internal field, which is actually very strong, and the external field, sum of both of those. Okay? And according to this theory, that internal field, if you denote it by the symbol Hi, that is directly proportional to the magnetization. Hi is proportional to M. So the net effective magnetic intensity at a point inside a ferromagnetic material is not equal to the external magnetic field H, but it is the sum of the external magnetic field H and the internal magnetic field Hi. Okay? So you can see I have mentioned here, in order to account for the special properties of ferromagnetic, Weiss gave a molecular field theory in 1907. And to explain the condition for a spontaneous magnetization, he assumed that in addition to the applied magnetic field intensity H, there is a strong internal field, and that strong internal field is actually proportional to the magnetization M. Okay? And on the line of Langevin theory, assuming this internal field, Weiss has developed his theory in 1907. So you can see, if you assume that Hi is the internal magnetic field, then this Hi is proportional to M in accordance with Weiss' idea. And so Hi is given as lambda times N. Actually here, this lambda is a number which is called Weiss factor. This is called Weiss factor. Okay. So now if you talk about a point inside a ferromagnetic material, now you can see there will be two fields there. One is the external field H and another is the internal field Hi. So the net effective field at an internal point given by this symbol He is equal to H plus Hi. Here H is the external field and Hi is the internal field. But you have seen that this Hi is lambda times M. So He is equal to H plus lambda M. Okay. So now what we have actually done, after assuming this internal field and finding the effective value of magnetic field inside a point in a ferromagnetic material, Weiss has done nothing else. He used the result of the magnetization obtained for a paramagnetic substance in case of Langevin theory directly. What will be the difference? He only replaced the term H by He. Okay? This will be the only difference. Where there will be H, that must be replaced by He if you are talking about the Weiss theory of ferromagnetism. So actually, Weiss theory of ferromagnetism is nothing. This is simply the Langevin theory of paramagnetism. Only you have to replace the external magnetic field H in the expression in Langevin theory by this effective magnetic field He. Okay? Now, you have already studied Langevin theory of paramagnetism in my previous video. So I think you must remember those results. So I have not derived that result here, but we have already learned this. So you have learned that according to Langevin theory, the magnetization is given by ms times L of A. Okay? Where you know this ms is called saturation magnetization, and this is the maximum magnetization acquired by a magnetic material, and this is given by n times mu, where n is actually the number of atomic dipoles or number of atoms or particles or molecules in the unit volume of the specimen, and mu is the dipole moment or magnetic moment of each atom. Okay, so n times mu, this is equal to ms, and that is called saturation magnetization. Okay, and what is this L of A? You know, you have already studied this. This is called Langevin function. And how this Langevin function is defined? We have seen that this Langevin function is defined as L of A equal to cot hyperbolic A minus 1 over A. Okay? And what is this A? You have to remember. You have already studied this in Langevin theory. A is given as this, like this, mu h over kb times t. Okay? Where you know mu is the magnetic moment of each atomic dipoles or each atom, you can say, and h is the external magnetic field, kb is the Boltzmann constant, and t is temperature. Okay, all these results I have directly written here because we have already learned these things in the Langevin theory of paramagnetism previously. Okay, actually Weiss has written the same expression for magnetization in case of ferromagnetic material too. As I have told you earlier, that Weiss have developed the theory of ferromagnetism on the line of Langevin theory of paramagnetism. So this expression for magnetization was directly applied for ferromagnetic material too by Weiss. Okay? So in this case too, M is given by ms times L of A. But when you will write the expression for A, then you must replace this H in Langevin theory by He in this Weiss theory. Okay? As I have told you earlier. And you have seen that this effective magnetic field is given by H plus lambda m. So when H will in this expression will be replaced by H plus lambda m, then this expression will become the value of A in case of ferromagnetic material. Okay? So symbol is A, but value has been changed. You can see. This is mu times H plus lambda m over kBt. Okay? Now again remember the results of Weiss theory. We have actually discussed the Langevin function in two cases, in two situations. First of all, you have considered that temperature is high and the field is small. In that case, we have seen that this factor A is tending towards 0, and you have obtained that in that condition, this L of A is equal to A by 3. Okay? And when temperature was low and field was high, then A was actually equal to 1. Then Langevin function was 1 and A was tending towards infinity. Okay? I have considered here high temperature and a small field, and remember in this condition our Langevin function is equal to A over 3. Okay? And so if L of A is A over 3, then you can see the magnetization M will be given by this equation 1. This is ms times L of A, but in this very condition, since L of A is A by 3, so M will be equal to ms times A over 3. Okay? But you know, ms, which is saturation magnetization, or you can say this is the maximum magnetization. And this maximum magnetization is given by mu times n. because n is the number of atoms or molecules or atomic dipoles in unit volume of the substance, and mu is the magnetic moment of each molecule or each atom. Okay. And A, as you can see this equation 2 here, is equal to this much. So m is given as mu into n times mu times h plus lambda m over 3 kBt. Okay. So this is the expression for magnetization of a ferromagnetic material when it is placed in an external magnetic field H at a temperature T. Now, actually simplifying this result, we will obtain the value of this magnetization. Okay. So you can see this is m equal to n mu square h plus lambda m over 3 kBt. Actually, I have multiplied by this factor mu n to the terms inside the bracket, and so this is this much. Now you can see m is in LHS and m is also in RHS. So we must simplify this result to find the value of m. And let us make the cross multiplication. You can see this is m times 3 kBt, and that is equal to n mu square h plus n mu square lambda m. Now bring this term containing m in LHS and take it as a common factor. So you can see when we will take m as a common factor, the remaining term is 3 kBt minus n mu square lambda, and that's equal to n mu square h. Are you getting the things? Definitely you are getting the thing, because this is a very simple calculation. Okay. And so you can say that m is equal to this much. Here in denominator I have taken this 3 kb as a common factor. Okay. So the remaining term will be T minus n mu square lambda over 3 kb. Okay. So this is the expression for the magnetization of a ferromagnetic material. Now you know, once we have an expression for magnetization, then easily we can find the expression for the magnetic susceptibility, because the magnetic susceptibility chi, you know, this is simply m over h. So see this equation 3 and divide this m in LHS by this h in RHS, and so this chi will be equal to this much. It is very easy to understand. This is n mu square over 3 kb times T minus n mu square lambda over 3 kb. Okay? And this expression can be written as chi equal to C over T minus Tc. Now mark, this C has been written instead of this n mu square over 3 kb. Okay? And this Tc, which will have actually the dimension of temperature, that has been written instead of n mu square lambda over 3 kb. Actually this temperature Tc is called the Curie's temperature for the given material. It will have different value for different material. Okay, so this is a constant for a particular material. For different material its value will be different. Okay, actually this equation 4 is known as Curie-Weiss law. This is called Curie-Weiss law. You know, we have seen the Curie law in paramagnetism, that this is given by chi equal to C over T. Now, so this Curie law has been just modified in case of ferromagnetic material, and this is in the form C over chi equal to C over T minus Tc, where Tc is this much, which is called Curie's temperature. Okay. So I have mentioned here, you can see that this equation is known as Curie-Weiss law. It is obeyed by ferromagnetic substances above certain temperature given by this Tc, not theta c but Tc. Okay. Actually see, when temperature T is greater than this Tc, T is greater than this Tc, okay, then chi will be positive. And so this law is obeyed. Chi must be positive for ferromagnetic material. So this law is obeyed only when the temperature is greater than this Tc. Okay. Now, as I have told you that the prime aim of Weiss theory, or even the quantum mechanical theory which we will learn later on, in case of ferromagnetism, is to explain its spontaneous magnetization. How you can say that when the magnetizing field is removed, even after the removal of magnetizing field, the magnetization not vanishes, but some magnetization remains in the material. So this is the basic fact which must explain our theory. So now let us see how we can explain this spontaneous magnetization on the basis of this Weiss theory. Okay? You know, spontaneous magnetization means what? This is magnetization in absence of the magnetizing field H. That is when you make H equal to 0, that is external magnetic field equal to 0, then what is the value of M? That is called actually the spontaneous magnetization. So for getting the value of spontaneous magnetization, we will have to see this particular equation which I have defined in equation 2 for A. You can see A is equal to this much. This is mu times H plus lambda M over kBt. Okay. Now, if your aim is to find the value of this magnetization M when H is equal to 0, then how we can find? For this, let us simplify this equation. You can see A is equal to this much. I have written this equation previously. Okay. And so, from here, you can see that H plus lambda M will be equal to A kBt over mu. Okay. And so, lambda times M is equal to A kBt over mu minus H. Okay. This is the expression for lambda times M, where M is the magnetization in general and lambda is Weiss factor. Now, for getting the value of a spontaneous magnetization, what we will have to do? You have to take H equal to 0, because you know when external magnetic field is removed, then what is the magnetization remaining in the specimen? That is a spontaneous magnetization. So to get the value of a spontaneous magnetization, we must make H equal to 0. So after making H equal to 0, this equation 4 will give you the value of a spontaneous magnetization. Okay. Then M will be called a spontaneous magnetization. So you can see when H is 0, then lambda M is equal to what? This is A kBt over mu. And so M is equal to this much. This is A kBt over mu lambda. Actually, I have not changed the symbol, but in this equation 5, this symbol M represents the spontaneous magnetization. This is not magnetization in general. This is called a spontaneous magnetization. Okay? Because this value of magnetization has been obtained by taking H equal to 0. So, when H is 0, then M is not 0, but M is equal to this much. And therefore, this value of M is called a spontaneous magnetization. Okay? Now, actually, we will see how when this spontaneous magnetization can exist and when it does not exist. For getting the idea of this spontaneous magnetization, okay, we have to actually see some calculation, some graphical plot, and from that we can easily explain the existence of this spontaneous magnetization, when it will exist or when it will not exist. Now see, if you find the ratio of M and Ms, mark it. Here M is the spontaneous magnetization, and MS is the saturation magnetization. MS is saturation magnetization, and M in numerator, this is actually the this is a spontaneous magnetization. And you know, you have seen this in this equation 5, that this M is equal to A kBT over mu lambda. Okay, and MS is equal to mu n. MS is equal to mu n. So when you will substitute this value of M and MS, then you will get the ratio of M and MS. And that ratio, you can see the equation number 6, that can be obtained easily. Okay. Now let us see. As we have learned earlier, that this Tc, which is called actually Curie temperature, that is equal to mu square n lambda over 3 kb. So after making the use of this expression for Tc in this equation 6, you can easily see that M over Ms is equal to A over 3 times T over Tc. Okay. This is simple algebra. In other words, you can also say that M is equal to Ms times At over 3 Tc. Okay. So this is the relation between the spontaneous magnetization M and the saturation magnetization Ms. Okay. Now let us see the general expression for magnetization. Okay, that is whether the field is 0 or field is not 0. Actually, there is a shivering cold, so actually my staff has given me a cup of tea, and so you have learned some horrible sound, so don't mind, because our door was closed, and when I have opened it, then there was a very loud sound. Now it is okay, because due to cold I have actually demanded a cup of tea, because my throat is not working properly. Sorry. Now let us see. M is equal to Ms times La in general. Here the symbol is M in numerator, but don't think that this is a spontaneous magnetization. This is magnetization in general. I have not changed the symbol. Okay, but Ms is again the spontaneous magnetization. Okay, so M over Ms is equal to L of A. So there are two equations. First one is M over Ms equal to A over 3 T by Tc. In this equation, the symbol M in numerator actually represents the spontaneous magnetization. Okay, and in equation 8, the symbol M in numerator does not represent a spontaneous magnetization, but it represents magnetization in general. Okay. Now let us plot the graph of M over Ms in against of A. Okay. Let us see this equation 7. M over Ms equal to A over 3 times T over Tc. This can be written as M over Ms equal to A over 3 Tc, okay, times T. Sorry. This is M over Ms, okay, T over 3 Tc times A. Oh. And so this is nothing, this is simply an equation of a straight line, y equal to mx. This represents a straight line passing through the origin having slope t over 3tc. And you can see this straight line which I have shown in this figure by this in this figure. You can see this is the graphical plot of that equation 7. Okay, and we get a straight line. This is the equation of a straight line, and its slope, you can see I have shown in this figure, is tan inverse t over 3tc. Okay, now when m over ms is plotted in against of A on the basis of this equation 8, you have learnt in paramagnetic Lenzman theory of paramagnetism that this graphical plot is just a curved line, as you can see in this figure. This is called Lenzman curve, LA. Okay, this is called Lenzman curve. Okay, and at the origin, that is where A is equal to 0, there actually the slope of this Lenzman curve we have learnt earlier in Lenzman theory, that the slope of this Lenzman curve at the origin, that is where A is equal to 0, is tan inverse 1 by 3. Tan inverse 1 by 3. Now you can see both of these equations, that is equation 8 and equation 7, both equations will be, when both of these two equations will be satisfied simultaneously, only then a spontaneous magnetization will exist. So we can say that for spontaneous magnetization, both of the equations 7 and 8 must be satisfied simultaneously. Okay, actually graphically, what will be the required condition for this? In fact, graphically the required condition is given by the intersection of the plots of equation 7 and that of equation 8. Okay, the line given by this equation 7 or you can say by this equation actually intersects the Lenzman curve at 2 points. You can see at the origin and at this point P. Okay, at these 2 points this line actually intersects the Lenzman curve. Okay, now the point P will exist, this point P, that will exist only when the slope of the line given by this equation m by ms equal to t by 3tca, that is equation 7, will be less than the slope of the Lenzman curve. You can see the slope of this line is when will be smaller than the Lenzman curve, only then this intersection at point P is possible. Okay, and so you can say since the slope here is of the Lenzman curve at the origin is tan inverse 1 by 3. Okay, so you can say that there will be a spontaneous magnetization only when the slope, that is inclination, you can say t over 3tc is less than 1 by 3. Only then a spontaneous magnetization will exist. Okay, and this 3 and 3 will cancel and you can say that t is less than tc. So what is the required condition for the spontaneous magnetization? You can see, you can say that Tc is the temperature below which a spontaneous magnetization will exist, or our material show the spontaneous magnetization. Okay, but if a situation is just reverse, that is T is greater than Tc, the material does not exhibit a spontaneous magnetization. Actually, in that very condition, our material behaves like a paramagnetic substance. So you can say that a ferromagnetic substance behaves like a paramagnetic substance above the Curie temperature, Below Curie temperature, the material behaves as a ferromagnetic substance. But above Curie temperature, when the temperature is made greater than Curie temperature, the ferromagnetic substance suffer a second order phase transition and it behaves like a paramagnetic substance. So transition of ferromagnetic substance into the paramagnetic substance as Curie temperature is a second order phase transition. Okay, and you have learned this thing in superconducting superconductor chapter 2. Okay, so I think now the idea of Weiss theory for ferromagnetism, how this theory explains the spontaneous magnetization, is very clear to you. Okay, thank you very much.